Hello friends, I welcome you in lecture number 22 on vector calculus. In this lecture we will discuss one more question on Green's theorem. This question was asked in GTU Winter 2021 exam for 7 marks. The question is, verify Green's theorem for the function f bar equal to x plus yi plus 2xyj and C is the rectangle in the xy plane bounded by the lines x equal to 0, y equal to 0, x equal to a and y equal to b. Here we have to verify Green's theorem and it is not specified that which form we have to verify. So whenever it is not specified, we will use tangential form of Green's theorem, which is also known as circulation form. And the tangential form for Green's theorem is if f bar is having components m and n, if f bar equal to mi plus nj and C is a closed path in xy plane which encloses a region R in the xy plane, then line integral m dx plus n dy along curve C is given by double integral over this region R of the function del n by del x minus del m by del y integral with respect to area. dA can be dy into dx or dx into dy according to our choice. It is our decision whether we want to integrate with respect to y first or with respect to x first. And here we are asked to verify Green's theorem. So we have to compute line integral as well as double integral, and we have to verify that both of these integrals are equal. So first we denote these components by capital M and capital N. We have f bar equal to x plus yi plus 2xyj. We denote coefficient of I by capital M. Let capital M equal to x plus y and capital N equal to 2xy. And we will require the curve which is a rectangle, and we will require the region enclosed by the curve. So it is better that first we sketch the region of integration and its boundary, which is a rectangle. So for that we first consider this, suppose this is y-axis, this is x-axis, and two lines are x equal to 0 and y equal to 0, that is x-axis and y-axis are given. So y-axis means x equal to 0 and x-axis is represented by y equal to 0. Other two lines are x equal to a and y equal to b, and suppose we consider a and b as positive, then x equal to a means line parallel to y-axis. So here suppose this much distance is a, then this line will be x equal to a, line parallel to y-axis. So this is the line x equal to a. Suppose this much distance is a, then this point is a0, this is origin. Similarly, suppose this much distance is b, then line parallel to x-axis is y equal to b. So this line is y equal to b if this much distance is b, and this point will be 0b. This point will be here up to this, x is a and y is b. So this is the point AB, and region of integration is region bounded by this 4 line segments, or interior of the rectangle is the region R of integration. So double integral will be considered over this region R, which is a rectangle, and boundary of this region is our curve C. So curve C is the union of 4 line segments. So curve C has different representations along all these different line segments, and we have to compute line integral as well as double integral. So first we compute line integral, and we can see our curve C is the union of these 4 curves, which we denote by C1, C2, C3 and C4. The representation for C1 is y equal to 0, because we have to consider this line segment and it is on x-axis. On x-axis value of y is 0, therefore dy will be equal to 0, and here x is starting from 0 and we are going up to this. So x varies from x equal to 0 to x equal to a. Now along path C2, x is constant, that is x equal to a, and therefore dx will be equal to 0, and y varies from 0 to b. C2 is starting from this point, at this point y is 0, C2 ends at this point y is b. Similarly, equation for C3 is y equal to b. So here we write y equal to b, and therefore dy will be equal to 0, and x is varying from x equal to a to x equal to 0. So here x is from a to x equal to 0. We are moving along this direction. So this is the starting point of C3. At this point value of x is a, at this point value of x is 0, and finally C4 is on y-axis. So on C4 x is 0, therefore dx is 0, and we are moving in this direction. At this point y is b, at this point y is 0. So y is from y equal to b to y equal to 0. Now our integral is line integral is m dx plus n dy over curve C, and because curve C is the union of 4 line segments C1, C2, C3 and C4, our curve C is the union of C1, C2, C3 and C4. Therefore line integral along C will be equal to sum of line integral along each of these 4 curves. So this I can rewrite as in line integral along C. Before writing this as a sum of integrals, first we substitute values of m and n. M is x plus y and n is 2xy. So here we write m equal to x plus y and n is 2xy, x plus y dx plus 2xy dy. Now this is equal to integral over C1 x plus y dx plus 2xy dy plus integral along C2, this is same x plus y dx plus 2xy dy plus integral over C3 of x plus y dx plus 2xy dy, and finally integral along C4 x plus y dx plus 2xy dy. Now we substitute for each of these curves. First we see what is representation for curve C1. So along curve C1 we have y equal to 0, that is dy equal to 0, and x is from 0 to a. So along C1 limits of x are from 0 to a, and along C1 y and dy are 0. So along C1 dy is 0, therefore this term is 0, y is also 0, so we are left with x dx. So here we write x dx. Then we go for second line segment, which we have denoted by C2, and along C2 x is constant and dx is 0, y is varying from 0 to b. So x equal to a, dx is 0, y is from 0 to b. So first we put limits, y is from 0 to b and dx is 0, therefore this part becomes 0, and x is a, so this is 2ay dy. Here we write 2ay dy. This is for curve C2 or second line segment. Now we go for C3. So along C3 we have y equal to constant, therefore dy is 0. So dy is 0, y equal to b, x is from a to 0. So first we write limits for x, x is from a to 0 and dy is 0, therefore this part is 0, and y is b. So here we have x plus b dx, and finally we write for C4. Along C4 x is 0. Along C4 we have x equal to 0, therefore dx is 0 and y is from b to 0. So here we write y from b to 0, x is 0 and dx is 0, and because x is 0 we have 0 here. Along C4 x is 0, dx is 0, and because dx is 0, this term is 0, because x is 0, this term is 0. So now we have to integrate this portion only, and this is equal to integral of x is x square by 2, limits of x are from x equal to 0 to x equal to a, plus 2a into integral of y is y square by 2, so this 2 will cancel out, and limits of y are from y equal to 0 to y equal to b, plus integral of x is x square by 2 plus b into x, limits of x are from x equal to a to x equal to 0. Now we put upper limit and lower limit for each of the integrals. Upper limit is x equal to a, and here we have a square by 2 minus 0, that we are not writing. Similarly upper limit is y equal to b, so here we have a into b square minus 0, so that also we are not writing, plus x equal to 0 minus x equal to a. So first we write for upper limit we have 0 minus, if we put x equal to a, we have a square by 2 plus a into b. Now we simplify this, so we can see this a square by 2 will cancel out, and we are left with ab square minus ab, and if we take ab common, we are left with b here, and there is 1 here. So line integral has value a into b times b minus 1, therefore line integral along given closed path is m dx plus n dy equal to a into b times b minus 1. So we give this number 1, and now we try to evaluate double integral over this region R. Now because we are having rectangular region, limits of double integral will be constant. So here, because we are having rectangular region, we can observe that x is running from 0 to a and y is running from 0 to b. So limits of integration for double integral will be constant, because we have a rectangular region. X varies from 0 to a, y varies from 0 to b, and we will decide this portion del n by del x minus del m by del y. Del n by del x means derivative of x with respect to x considering 2y as constant. So 2y constant, derivative of x is 1, minus del m by del y means derivative of x, which is 0, derivative of y. So del n by del x minus del m by del y is 2y minus 1, and limits of x and y are from x is from 0 to a, y is from 0 to b. So now we evaluate that double integral over r del n by del x minus del m by del y. Suppose we decide to integrate with respect to y first, then this is equal to double integral over 2y minus 1, which we just computed, dy dx. Y has limits from 0 to b, x has limits from 0 to a. So we have substituted this value, del n by del x minus del m by del y equal to 2y minus 1, and along this rectangle x is from 0 to a, y is from 0 to b. Now we try to evaluate this double integral. First integral is with respect to y. So while doing that integral, we will consider x as constant. So this is equal to x is from 0 to a, and integral of 2y is 2 into y square by 2. So I write only y square minus y, and y has limits from y equal to 0 to y equal to b. So first we put y equal to b, and this is as it is. If we put y equal to b, we have b square minus b, and for y equal to 0, this will become 0, integral with respect to x. So this we can take outside, b square minus b into integral of x. Integral of 1 with respect to x is x. X is from 0 to a, and here also we can take b common, and we are left with b minus 1. Here we are left with a minus 0. So this is ab times b minus 1. So double integral has also same value, double integral over r del n by del x minus del m by del y is ab into b minus 1. So we give this number 2, and let's compare with equation number 1. Here also we get the same answer, ab into b minus 1, and here also. So we can write from 1 and 2. From equation number 1 and 2, we observe that line integral m dx plus n dy along a closed path C that encloses some region R in the xy plane. So this line integral can be obtained by evaluating this double integral, del n by del x minus del m by del y, either dy dx or dx dy. So this is very important result, and we have verified that both of these are having same value, ab into b minus 1, and therefore we can say that Green's theorem is verified. So if they ask you to verify the result, you must compute line integral as well as double integral. But suppose this question is to obtain the value of line integral. Suppose instead of verify, they ask you to apply Green's theorem to obtain the integral of this vector field. So in that case, either you can use line integral or double integral as per your convenience. So in that case, you don't have to write both the parts. But whenever you have verification part, if they ask you to verify, you must compute with your method, and you must go in this way also. So first we computed line integral, and we find that line integral has the value ab into b minus 1. Then we computed double integral, and we obtained the same answer. Therefore we can say that Green's theorem is verified. So this is all about this session. I hope you like it. Thanks for